talk is Bucks, and it's another video, but I think Bucks is also here for questions at the end. So let me try and share the video. Start with. And we'll make it full screen. Okay.
Thank you, Tony, for the invitation to speak at this meeting in honor of Richard Brak. I met Richard 25 years ago when he was collaborating with Stu Whittington on directed models and using those as models of polymers. Richard's work in this area, not only then but subsequently, has hugely influenced my own thinking about the use of directed path models in polymer physics. And I have, with collaborators over the years, made contributions to this area. Now, I won't talk today about the directed path model, but I will definitely keep in mind that Richard had a huge impact in this field, and that his untimely death is a loss not only for his friends and colleagues, but also a loss in a greater sense as an academic who still had much to offer in his area of expertise. Now, what I will talk about are models of branch polymers. And see, these are uniform branch polymers, and in particular models with the two following geometries. So we will have a star polymer here, which is being pulled by a force in its central node, and the arms of the star polymer are all ending in an adsorbing plane. So this is a hard wall, and the endpoints of these arms of the star are constrained to live in this hard wall, in the surface of this hard wall. One of these would be the origin, and then of course the other endpoints here are free to move around horizontally in this adsorbing plane, but can't leave it. So we call these configurations spiders, and in particular F spiders if they have F arms, or in this case I guess it's more appropriate to call them legs. The other model I will mention towards the end is that of a watermelon graph, where you have two nodes joined by branches running between them in the following connected geometry. So they look like this. Now, in both these models, the arms or the legs or the branches are self-avoiding walks, and we will analyze the free energy of these models when they are both being pulled by forces at the central nodes, and in this case also when it's absorbing. And I want in particular to focus on the techniques that one uses to analyze these models. Now, Stu already talked about pulled adsorbing self-avoiding walks. So here's the basic model. There's an adsorbing plane. There's a self-avoiding walk attached here at the origin, and then it runs off into the half space above the plane. Whenever it visits the plane, so a return here, it binds with an energy epsilon to the plane, and we say that such a vertex is adsorbed. And of course there's a last vertex where it's adsorbed, and then there's a tail running off into bulk up to its endpoint, and at this endpoint there's a force pulling it vertically. So these are pulled adsorbing self-avoiding walks, and the number of conformations of such walks I will indicate by Cn, of V, which is the number of visits to the adsorbing plane, and H is the height of this endpoint. And I will introduce two activities, Y and A, which are related to the pulling force F and to the binding energy epsilon. And what we'll do is we'll put together a partition function, which is sum of all the states weighted by the appropriate Boltzmann factors here. So A to the V, Y to the H. And it is known that the adsorbing walks free energy and pulled walks free energy are defined for this model. So for example, if you put y here equal to 1, which is a zero force, you get the absorbing walk sphere energy kappa of A. And if epsilon here is 0, but F is not 0, then you get the pulled walk sphere energy, which we indicate by lambda, and they're given by these two limits. It is also a result that the limiting energy of the model, when it's both being pulled and it is absorbing, is given by psi of a y, which is just the maximum of kappa and lambda. The way one proves these results is by using techniques developed in a paper by Hammersley, Torrey and Whittington in 1982. Now, we have over the last 5 to 6, 7 years maybe, Stu and I have worked on models similar to this but with different connectivities. So we've looked, for example, at F-stars, tadpoles, dumbbells, a T-comb and a ring in the context of it being absorbing and being pulled by a force. And the phase diagram in each of these cases were found to contain a free phase where the branched configuration floats off into bulk, or when it's absorbed, it tends to stay close to the absorbing line, or it's ballistic, where the force pulling it removes it from the absorbing plane, and then it's the distance between the endpoint where it's being pulled and the plane is of order n, if the size of the model is n. The partition of these models are all given in the same way as for pulled and absorbing walks, and similarly free energies are known to exist. Now we have shown in a variety of different cases what the free energies are, and I just list them here briefly in the case where there is no absorption. So these free energies here. So in the case when there's no absorption, you can easily show, it's not easily show, you have to be quite careful in fact, but you can show that the free energy is given by these expressions in terms of the free energy lambda of a pulled walk. If A is not equal to 0, you get slightly more complicated expressions, but in principle it's all known. The one we'll be interested in is in fact this last one, the polygon free energy. So a polygon is attached here to the surface, it's being pulled by a force F, and the free energy turns out to be lambda y to the power 1/2, as the force is mediated equally along the two arms, or the two sides of this polygon, into this vertex where it's attached to the absorbing plane. Now we're going to look at F spiders, which has this geometry, as I've explained. So it's pulled here in its central node or middle vertex. The free energy, and I'll give that away at this point, is given by lambda y to the 1/f. And what I want to do in this talk is just to give you a very brief outline of the proof. The methods that you use to prove this result, that this is the free energy in the case that there's no absorption, is based on pioneering work of Chrysoteros, stretching back as long ago as the 1990s, and consists of strategy bounds that one uses, unfolded walks, walks in wedges, and then most importantly, most popular arguments. This is really a most popular class argument, but the argument itself is a very powerful argument, and in fact should be popular in this field when one works in these types of models. Here are more ingredients. So we'll focus certainly on pulled walks. So you pull a walk at its endpoint here, and it's attached at the origin here. And you can unfold this pulled walk. So you fold it in the horizontal direction to get what's called a pulled bridge. And pulled bridges will be a critical aspect of how we go about proving that for a pulled spider, you get the free energy lambda y to the 1/f. In addition to pulled bridges, we'll also look at absorbing loops, from which we will be creating the pieces of the legs of the spiders which are in fact absorbing. Here are the free energies in these cases. So the free energy of pulled walks, of course, is lambda of y. This does not change when you unfold the walk horizontally. And then for a adsorbing loop, the free energy is kappa of A, which is the same as the free energy of an adsorbing walk. If you look at these structures, you can define or you can find most popular heights and most popular visits in each of them. So here the height of this node being pulled is h, and it may have one of n plus 1 values. So the height may be 0 or 1 or 2. Certainly in the partition function you have the sum over all the heights. But in that partition function, for a given y, so for a given pulling force, there is a most popular class of walks at height h star which dominates the partition function. And you can only focus in calculating the partition function on the class of walks with this most popular height h star. Certainly for bridges there's the same kind of most popular height. I don't know if it's the same as for walks, maybe it is, I don't think that's something that's known. And then when you do the adsorption of a loop, there's a certain number of visits in the adsorbing plane, which are bound to the adsorbing plane. That gives you your weight in the partition function, and once again there's a certain value, V star, the number of visits, which is optimal if you wish, or where Ln of V star dominates the partition function. And so these most popular heights and visits H star and V star is something we will work with. So for example, in the case of the pulled walk, or the pulled bridges in this case, here is the partition function. So that piece is the partition function. There is a value H star where this single term, Bn H star y to the H star, dominates the sum, and certainly the n-going infinity limit will give you lambda of y, so that we get that lambda of y is in fact equal to this, where we've just dropped the summation and replaced h by a star. And so h star would be the dominant term in the summation, and the similar thing goes for kappa. Now let us look how we use this. So what we're going to do to construct a spider is to make small wedges, and inside these wedges we're going to build the legs. And as we build the legs, we're going to put together bridges in the wedge and loops in the wedge, and then these will form one of the legs of the spider, and then we're going to put a number of wedges together around the central node to create the full spider, and in fact to get the lower bound on its free energy. An upper bound on the free energy would be easier to obtain, and we will show that later. But let's first focus on the lower bound and how you construct a spider so that you can get the lower bound out of the construction. The important thing we need to know is the number of adsorbing loops inside what I call an alpha wedge. So this is a wedge which looks like a pie slice, or a cake slice more properly, where the loop is attached at the origin, which is at the vertex of the wedge, and then it goes inside the wedge and then ends again in the bottom plane of the wedge. So this would be the number of unfolded loops of length n, and with v visits to that bottom plane. The loop partition function I will indicate by an sub alpha of a. So this is the partition function of loops, and what we're going to do is we're going to count some of the contribution to an, to this partition function, so that we come from below and get a lower bound on it. The way we do it is we take loops. So here I have a loop. So here I have a loop of length m inside the square lattice, or the cubic lattice, and its endpoints are living in the xy plane. So its length is m, its endpoints are inside, are on the xy plane, and the number of visits is the most popular class, it's the most popular value of the number of visits, which I call V star. So I'm going to take capital M of these loops and put them together in a string like this. So there are M of these. So let me try to make an M. So there are M of these loops put together. You can't fit them inside the wedge unless you are sufficiently far away from the vertex of the wedge, which is here, the origin. So you have to move them along the wedge a certain distance away before they fit inside that wedge. And of course, the narrower alpha is, so the smaller the wedge angle alpha is, the narrower the wedge. And so you can think of this as the spine of the wedge. This is its bottom plane. And then you move these along away from the origin until they fit right inside the wedge. And then you join them with a string here, or a sequence of n steps from the origin to the first vertex here of the sequence of loops. So you put them together like this, and this of course now altogether is a loop itself, made up of these subloops or smaller loops and this sequence or the string of steps, and it contributes to this partition function. Now the most popular classes I'm using here, of course, so for each of these has limiting free energy kappa of alpha. And the way I've put these together to make a loop inside the wedge gives you this inequality. So these inequalities. Here are the weights from the M, the capital M loops that I've put into a string. All of these together is part with the partition function an of alpha a. So it's less than or equal to this because this is a term inside that partition function. And then of course there is the partition function here where you don't have a wedge. So this one, the wedge is gone. In this one the wedge is there. And this is the contribution of this string of loops inside the wedge. Now what you do is you take the logs of this. So you take the logarithms of this, and it gives you, after the division by m times m, it gives you the string of inequalities, and then you first take m to infinity, so the number of these loops to infinity, and then after that you can take little m to infinity, and that gives you this critical result, which is that adsorbing loops inside the wedge has free energy kappa of alpha, or kappa of a. Now you do the same for bridges. I'm not going to explain this very carefully as I did with the adsorbing loops, but what you do here is you take small bridges and you put them together again in a sequence here. You connect them to the spine of the wedge and to the bottom of the wedge by strings of edges, and you use the most popular classes to populate these sub-bridges. And then in the alpha wedge, this gives you a string of inequalities, which is rather similar to the one we had for adsorbing loops. And if you then take the logs of this, you divide by m times m, you take the n to infinity, you see that for a pulled loop, or for a pulled bridge inside the wedge, you can get the limiting free energy of pulled walks. You get lambda of y. So those are two subcomponents. Now how are you going to do this? You have to create adsorbing and pulled bridges in wedges. So this is your first step. You're going to put the bridges and the loops together to create adsorbing and pulled bridges in wedges, and then you're going to show that the limiting free energy of those pulled bridges inside the wedge is still psi of a y, which is the max of kappa lambda. And then you put these separate absorbing and pulled bridges in wedges together around a central node to create your spider. So here I'm creating the the pulled anti-adsorbing bridge, and you can see it's consisting of two components. There's first of all this part here, which is a pulled bridge, and then there's a second part starting there going up to here, that is an adsorbing loop. So you concatenate those two together at this first visit here of the adsorbing loop, and then you have your bridge followed by a loop, and together they form an adsorbing and pulled bridge. The free energy of these I indicate by we've indicated on the previous slide to be psi of AY. And what we do then is we take these in these alpha wedges, we put them together. This is a top view, and in this top view you put them together in a spider, this being the spider partition functions. This is the spider partition function if it has f of these legs. In terms of the pulled bridge partition function, and here is a most popular height for the central node, and that's the most popular height you choose here. There's a y to the h star, which is the most popular height, and that is for the spiders. And if you now bring this together, you'll see that it gives you this equality here, where I factor this y to the h star inside the brackets. And then you can take the limit inferior on the left hand side, and that gives you psi, or something bigger than or equal to psi of a y to the power 1 over f. The upper bound, in the upper bound it's easier to get. What you do is you ignore intersections between the legs of the spider, and when you do that you get an inequality of this sort, where the partition function of f spiders is less than or equal to this summation here, where I've replaced h, the summation of h, by its most popular value in this sum. And so what you do is you take logs of this, you divide by nf, and you take n to infinity, and this gives you the upper bound on the spider free energy. And so putting this together with lower bound shows the existence of the free energy, and from that you can get the phase diagram. So there is a ballistic phase, a free phase, and adsorbed phase, and then there is this red line of first order phase transitions separating the adsorbed and ballistic phases. Transitions between the free and ballistic and free and adsorbed are presumably continuous transitions, although I don't think that is known. Now, just to conclude the talk very quickly, I want to just expand what I have for spiders into the watermelon model. So what we're going to define is only pulled spiders. So this is the number of spiders of length nf and height h. So this is one of these spiders here, and there's no adsorption, right? And so its free energy is lambda y to the 1 over f. I also will define the number of watermelons of length 2nf. So each of these branches of the watermelon has length 2n, and there are f of these branches. And the extent of the watermelon, of course, is the distance between these two nodes. Now, what you can notice, for example, is that the number of such watermelons is bound from above by the number of spiders, where you have double the length size, or you have legs of length 2n of h, and you do this by cutting the watermelon here in its bottom node, and then spread out the legs in the horizontal direction to get your spider. And so spiders are clearly more than there are watermelons. You have to make a little bit of an adjustment here. In fact, you should rather delete the last steps. So a little bit more care is taken, but it's not a difficult thing to do. Now, in a spider like this, there are most popular leg endpoint positions. So these are vectors where the endpoints of these legs live, and their most popular places. So ones which dominates the partition function as before. So B star would be the most popular positions of those leg endpoints. And when you use your most popular class argument, you see that this free energy lambda to the 1 over F is certainly equal to this limit over here, where I've replaced the spiders by spiders where I simply fix the endpoints of the legs at most popular positions. Now, having done that, is you can take your spiders with most popular leg positions B, and you can reflect or take a copy of it, flip it upside down, and then glue two spiders together, right? So here is one spider, and here's the other spider below the adsorbing line. The legs join up into branches of the watermelon because they have the same most popular positions when you just reflect in the XY plane. So this forms a subclass of watermelons, and if you now go through your most popular arguments, you see that the partition of the spiders of length 2NF, so this is when you cut the watermelon into a spider, is bigger than or equal to the partition of the watermelons, and that is bigger than or equal to 2 spiders, so that's where the square comes from, each with leg endpoints at most popular positions and then at most popular heights. So you take logarithms, you divide by 2NF, you take n to infinity, and you see that the watermelon free energy is also lambda y to the 1 over F. So this concludes my talk. I guess the most important aspect of the work here is to show that free energies are functions of the connectivity or the way in which these various branch polymers or uniform branch polymers are connected. The phase diagrams are quite interesting. They include first order and continuous transitions which meet at multi-critical points. And then in other work we have certainly shown that some copolymer spiders have mixed phases. So phases which are both the character of being adsorbed and ballistic. Tony, as a final word, thank you for the invitation to contribute to this meeting. I think it's a wonderful thing to do in memory of Richard, whose untimely death shocked all of us. Thank you.
Thanks very much for that talk, Bucks. So Bucks is having trouble with his sound. I don't know if he can hear us. Hopefully he can hear us. But he's requested if anybody has questions, just put them into the chat. You can't hear? Okay. All right. If anybody wants, so you mean try a question, Nathan, or? Oh, you were just saying he could hear us. I think he okay. Okay. He can hear. All right. So if anybody wants to try a question, I guess we could try that. Anybody online have a question for Bucks? No? Okay. All right. In that event, any questions here, Bucks? No? No. Okay. All right. Let's thank Bucks one more time. And everybody in that session. That was a good session. Thank you. And so we've got a coffee break now.